All right, good morning, everyone, and welcome to our NEACT Summer PD series. And today we are with Frank Gasparro, who is a native of Philadelphia and earned his bachelor's in chemistry from Villanova and his PhD from Princeton in physical chemistry. And after teaching at the university level for several years, he went on and did a lot of different research experiences in different positions. And since 2000, he's been teaching high school, first at West Hill High School and then Cheshire High School, and currently teaches at Hampden Hall Country Day School, where he gets his students involved in independent research projects. And he is here today to talk to us about a method for the determination of the entropy change for a reaction. This is a NEACT event, and we're glad you're all here. And if you haven't joined NEACT, I encourage you to do so. I'm Kristen Van Der Veen, and I am currently the president of NEACT, and we're really glad to see so many people here today. And Frank, I'm going to turn it over to you.
Thank you, Kristen. Good morning, everyone. It's really a pleasure to be here. I'm going to start out with a little anecdote about electrochemistry. It goes back a long time ago. Maybe some of you weren't even born yet. When I was in high school in the late 50s, I learned about electrolysis, and I was fascinated by it. I was so fascinated by it that I set up an electrolysis of aqueous sodium chloride and water using a 9-volt battery and some carbon electrodes from zinc cell batteries, the old-fashioned batteries, the only thing that existed then. And I would go to bed at night worrying that I was going to kill my family with the chlorine gas. Of course, the amount was in the milliliter levels, so it wasn't. I used to put it between the door. I've gotten involved in a lot of other things since then. My PhD thesis in spectroscopy. My research for many years dealt with photochemistry. But when I get to electrochemistry in either an honors chem, which I taught for a long time, I don't teach anymore, or an AP chem, it always tugged at my heartstrings, and I would always want to do more. So I'm putting up here, I'm sharing the screen, and this document is available, right, Kristen? You're muted.
It's in the calendar invitation, and I will put it in the document.
Okay.
For the summer.
So I was fortunate when I went into high school chemistry teaching, which was kind of a sudden event. I won't go into those details. That's the whole story. But when I got to Hampden Hall, I overlapped with a teacher who'd been there for 34 years. And I inherited many, many lab demos and lab write-ups, which we published in the lab manual. But this is one that I generated on my own. I think most people are familiar with this demo that you can do where you put a piece of zinc. You can see my pointer, right? Put a piece of zinc in copper nitrate and you can see a reaction occur. Well, I set up this lab to lead it along and asked what about the reverse reaction? What happens if we put copper and zinc? And we, of course, know that it doesn't happen. And they've heard about the reactivity series by the time we do this, so they should know that as well. I try to lead them on, asking lots of questions. What is the effect of using zinc powder? If you do this, of course, when you put a piece of zinc in copper nitrate, you can see it starting to darken. A reaction is obviously occurring, and it's not easy to tell that it's copper forming because in the microparticulate form of the deposition, it looks black, but eventually you can see red powder. Then we said, what's another way to do this? And we talk about electrochemical cells, which is the same overall net reaction. And I set one of these up, and we're going to see the setup today using some probes to measure voltage. As part of this, doing the lab, I asked them to do some pre-lab work, just recounting things they should know about already or from seeing the setup, what's the formulas for stuff? Zinc, zinc nitrate, copper, copper nitrate. What do they look like? And then finally, what observations do you make when you connect everything together? So in an electrochemical cell, you'll see a voltage. And of course, the key component, I call it the on-off switch, is the salt bridge. Take this off, put the salt bridge in, you get a voltage, take the salt bridge out, it's like an on-off switch, the voltage disappears. So this is background. A couple of years ago, I think it was two springs ago, I decided that it'd be fun to thinking about this. It'd be fun to measure the free energy by measuring the cell potential, but also do a thermochemistry reaction, a calorimetry reaction, where you can measure delta H. And then it dawned on me, if we know delta H and delta G, we can find delta S. Now, these numbers are not outstandingly accurate, but the point is there. So I am going to switch over to my PowerPoint now. I got to stop share. I got to remind myself what to do. Oh, look at all these people here. Welcome. Share screen. Where is it? Here it is. So I call this a method for determining the entropy change or reaction. Of course, we teach that entropy can't be measured. So I didn't say the measurement of entropy change, but determination. Okay. I forgot how I control PowerPoint. Oh, here we go. Here's what I want down here. So the handout is the one I was just talking about. And if you use the zinc strip and copper nitrate and try to measure the temperature, there's no appreciable temperature change. But the idea here is to set up a zinc copper electrochemical cell with their respective nitrate solutions and measure voltage and temperature. The overall reaction that occurs, of course, is a single replacement reaction. And I like to ask lots of questions, so let's get some participation. How can we speed up the reaction without catalysts? Use zinc powder. What observations are going to make? So one, here was this temperature change. I don't recall what these numbers were for what solution, but this was a modest amount of material. What are some other possible observations? So I'll answer the questions. One is you see the deposition on the zinc electrode. If you use zinc powder, you see a vigorous reaction, a fading of the blue color. And you might say, well, you should see the appearance of copper. With excess zinc, it's hard to see. But we have a remedy for that. This was a little setup that I did, quick and dirty, filtering the reaction after the zinc reacted with the copper nitrate. We can see the solution is colorless down here. I call this doing magic. My screen's in the way. Shoot, don't do that. There we go. I call it magic. That's what we called it before science. Somebody on the AP Chem Facebook page came up with that quote. I can't remember who it is now. But if you add HCl to the residue collected from the zinc powder reaction mixture, you're going to get a reaction. We all know that zinc reacts with HCl fairly readily. And if you carefully rinse this and look at the filter paper, you'll get what's on the next slide. Why is it not advancing? This is not easy to see. I don't know if anyone can see the reddish color in here. I see the most intensely up here. I guess I didn't get rid of all the zinc. So we can reveal that, yes, truly copper forms in that reaction. Extended goal for AP Chem, as I mentioned, was to find the entropy change with the single replace reaction using Hess's law for thermodynamic quantities, measuring E cell, the voltage, and doing calorimetry to determine the heat of the reaction and then converting it to an enthalpy by dividing by the number of moles. So here's the setup of the electrochemical cell. This was I decided to order some new copper and zinc because I've been using the same pieces of metal for a long time and they're slightly corroded. I thought I was going to get a chunk about 2 inches long. I got a chunk about 1 centimeter long, but I set them up with these alligator clips. And we can see the sodium nitrate, or I used potassium nitrate when I did the experiment most recently. And we see the blue copper solution, and that has the copper electrode dipping in it, and the color is zinc solution. And of course, when this is set up and running, there's no net reaction. This theoretically could stand for a long time because the cell potential measurement doesn't draw a current. It just measures the tendency for the reaction to happen. This is the effect of no salt bridges in here. Put the salt bridge in, you get a voltage. There's a little spike there because it took the salt bridge out, illustrating the on-off effect of the salt bridge. It's like on and off switch. This data is obtained using Vernier Lager Pro. I don't know how many people use that. I also use Pasco probes, but I haven't seen the electrode measuring probes for Pasco, but they may also have them. This is measuring the temperature change. This is whenever I did this experiment, I don't remember the exact date, but this is the solution with the temperature probe in it before adding the zinc. So this is just the copper nitrate solution. And as soon as you add the zinc, as soon as you add the zinc, you get a reaction. And there are little steps because of lags in stirring. How many people use these probes? Are people familiar with these, either Pasco or Vernier?
Mm-hmm.
Yeah. So this was another reaction that I did later on with a different solution. It had less copper nitrate. Here's a run I did just the other day, earlier this week, and I'm showing the reagents. I got lazy and I decided to buy the reagents from Flynn, 0.1 molar zinc nitrate, 0.1 molar copper 2 nitrate. And in the middle is a volumetric. This is conducted in a beaker to do the calorimetry. And this, again, this data is up from Lager Pro. This is a 4-degree change in temperature. If you look at this reaction, this is the contents of the reaction afterwards, and we see that this was adding zinc to copper nitrate, and clearly the blue color is gone, and there's an excess of zinc, so we got zinc sitting on the bottom and obscuring the copper. The calculations that are involved use the delta G equals minus NFE for cell, the Q calorimeter SM delta T. Of course, the reaction is the opposite of the calorimeter result, and delta H is Q reaction over N. So the way N is determined is from, since the zinc is excess, the amount of copper, the volume of copper times the molarity of the copper nitrate solution gives the number of moles that reacted. How do we get the entropy change? Solving and rearranging the Gibbs-Helmholtz equation. I think I did hopefully I did the algebra right here. And here's some data. Now, I have another sheet of standard state thermodynamic values at 298.5, and they include ions. These aren't often included. But if you take this is the enthalpy of formation of zinc, of course, is 0, copper 2 plus AQ, zinc 2 plus AQ, and copper. Free energy, ditto, 2 zeros again for the formation. Of course, entropy isn't 0, so they're values. Now, there's something puzzling that happens here. And I've checked my math, and I don't know how to, I don't know how to explain this. If you find delta G and delta H, you can solve for delta S and get that. But if you add up the enthalpies of the reactants and products, the entropies, I get a different number, 20.37. And I may it's a sign mistake, I'm not sure. Here's some experimental data we obtained. Now our voltage is a little low, and I've played around with this a lot to see if I can improve it. Yesterday, I calibrated the electrode using a freshly charged 9 volt, 1.5 volt battery. And these are experimental quantities based on measuring the temperature change for the calorimetric reaction, E cell that was measured, and this is the entropy. So it's in the ballpark. I would like to issue a challenge for anyone to go out and do this with your setup and see what kind of data the group gets. But I think regardless of the accuracy, of course, is important, but I think it illustrates the manipulation of thermodynamic quantities and as a way to find delta S. So what kind of principle illustrated here? Stoichiometry, limiting reactant, the effect of surface area on reaction kinetics, calorimetry. Now, to do calorimetry, you don't need a vernier Lager probe. If you have a decent digital thermometer, you can get fairly decent results. Cell potential, I guess you need some way of measuring that. A meter of some kind might also work. And then the determination of thermodynamic quantities, calculation, and then determination delta S. All this is carried out and while enhancing observational skills. So this is as you can see, a brief presentation, but I'm delighted to answer questions or talk about any other related issues.
What I really like about this, Frank, is that it really pulls a lot of skills together, and yet I imagine on the student end, it doesn't take that long to do. How long does it, right? Like
I would do this lab. I've had my students measure cell potentials in using those little beaker setups.
Right.
We have 40-minute lab periods. We can do several different combinations of metals, 3 or 4.
Mm-hmm.
If you add the calorimetry in, I think it would fill a 40 or 50-minute lab period.
Yeah.
Getting one run done. If multiple groups of students do the experiment, you could get a nice package of data.
Mm-hmm. Because I think that would be a fun lab to do, in AP at the end of your electrochemistry unit.
Yeah.
That's where I really see this fitting in well. Do you have a handout like of steps? We've got the handout. It was in the invitation that came out, the one Frank started with. Do you have a list of instructions for the students, or did you sort of just guide them through it?
I kind of guide them through it.
Okay.
I do use as a basis for a lot of labs the Vernier Lager Pro Lab Manual, and there's an experiment in there which I can share with people. I have a separate file on the lab. It's called Experiment 20. What's the? I don't remember the exact title, but I can get that to you so you can share it. And that has step-by-step way of doing it in little plastic dishes.
Mm-hmm.
Same idea. I like the beakers because you can see the chemicals better.
Right. But I also just love the idea that the student, we can measure entropy, right? We can, like we can actually pull it all together. It's not only this
Right.
abstract thing, we can actually get to it and show it.
Right. I was surprised that I did a little Googling around to see if anybody's, I haven't found anything like this. I can't believe no one else thought of it a lot sooner. I mean, it's kind of trivial in a way, but at the same time, at the level of high school, or even, I taught college chemistry for many years. We never measured or determined an entropy change for reaction. It's kind of like, you know, you can measure delta G, you can measure delta H, but delta S, nobody ever talks about it.
Mm-hmm.
How about some questions out there from all these people? Look at all these names out here.
Right.
Wow.
Laura.
There's one. Somehow my screen is dragging around. How do I do this? I unmute?
Laura's unmuted. Go ahead.
Oh, go ahead.
Hold on. Hi, how are you doing?
Hi, Laura.
Thank you for presenting today. I had two questions.
Okay.
One, when you show the kids the equations that they're using for delta G, the delta G equals NF, delta G equals minus NF E cell,
Yeah. Right.
and then the delta H equals Q of reaction over N. Do the kids find it difficult because is one N for the moles of eliminating reactant and the other N is for the moles of electrons that are transferred within the process? Do the kids find that confusing?
You know, in doing this with AP kids, no.
Okay.
I haven't done this lab with honor. I did the first part of the lab where I just measure cell potential and say, these are akin to batteries. I've done that with honor students, but we haven't done the calculations using N with, I should have put subscripts on those N's. I'm sorry, I didn't. I should have.
Well, this is going to be my first year in a long time teaching AP chemistry.
Yeah.
So I find it interesting, like they're using N, there are two ways of using N, right? And so that was interesting to me as
no, that's a good point. No, but in AP Chem, I haven't had that problem. I would think maybe in honors chem with some students, it might be a little confusing at first.
Mm-hmm.
But I would hope they would ask the question and then there would be the answer. Obviously, these are two different N's. N in the delta G equals minus NFE is number of electrons transferred in the reaction. Whereas in the thermochemical calculation for Q, it's the moles of stuff that reacted. So, but we use N a lot for lots of different things, and you always got to be careful. You're right.
Right. And then I guess the other question I had was on your slides, and I don't know if we're going to get to see this again, so I'm asking.
Yeah.
Your values for the ions, your thermodynamic values for the ions.
Yes.
Where did you find those?
You know, I did a Google search, and I was hoping to see it has no annotation on it of where it came from. I will do a new Google search and find it for you. It's a sheet of about there are 5 pages, mostly more common elements in alphabetical order. They don't have every element.
Okay. Okay.
A lot of metals, of course, but some other non-metals. I have up here at the top, I wrote the word source, question mark, because I didn't think to write it down when I found it on the by Googling. But I'm sure if I Google the title is Standard State Thermodynamic Values at 298.5. If I Google that, I'll find it. I will get that to Kristen so we can share with all the participants.
I'll post all the documents. I have to go back and do that for some of the other PB series we've done this summer, but I'll go back and I'll link all the documents I have into those so that everyone can access them.
Sounds good. Thank you for your question, Laura. You have more?
Yeah, I have one more. I'm sorry but you did answer I was going to ask about if those were standard states. Do you have any idea why? I mean, I don't know, being someone who's had some experience with electrochemistry, do you have any thoughts as to why entropy seems to be positive in this reaction?
Well, my guess is what I would attribute it to be. I would attribute it to hydration states of the 2 ions. Now, I did try to do a little research into that because I figured if the one ion had a greater charge density than the other, there might be stronger hydration and more ordering of water. The ionic radii are not, I couldn't find them. I did not find values for the ionic radii of copper 2 and zinc 2. Hard to believe, but maybe I just didn't Google hard enough. But I think it's probably about hydration energies.
Okay, thank you so much.
The strength of, and the ordering of water.
Yeah, okay.
You're welcome.
Thank you.
You're welcome, Laura. Now, this is one of the easier reactions to do. If you wanted to do other electrochemical reactions, I've used aluminum metal, zinc metal, nickel metal, and one other, aluminum, zinc. It's in the Vernier write-up that we're going to share with you. Let me share something else with you, going back to the original, this guy. I don't know if anybody caught this corner over here. It says what the objectives are: direct versus indirect redox, understand the chemical nature of a battery. And a battery in its simplest form, that should be singular, is constructed by two different metals, a conductive medium. Of course, we carry around a lot of battery-powered devices. And when I first came up with the idea of doing this lab demo, which is like not quite 20 years ago, but 17 or 18 years ago, I used to have the kids get out their cell phones and look what kind of battery they have. What kind of battery do people have? Let's see, I first started teaching in Hamden in 2004, 2005. The most common battery was a cadmium zinc battery, nickel cadmium battery. And I'm gonna really, hang on a second. I wish you could share multiple screens, but you can't. Anybody remember having a cell phone that looked, where'd it go? It disappeared. That's not it. Somebody wants to come in, let's admit them. That's not it. I don't know what that is. There must be something. I had the screen saved. Let me do a quick. I don't want to click there. All right. It's being recalcitrant. Here it is. Oh, here we go. Okay, I got it. Hang on, let me go back to Zoom. Uh-oh, I got Zoom here. How do I get to the menu? Okay, here we go, share screen. Anybody ever see a phone like that? That's a Motorola flip phone. It dates back to the early mid 90s, 95, 96. And being a techie kind of guy, I've been through lots of phones. I have a shoebox full of phones. And one of the points I'm making about showing them this phone is to look on the back and see what kind of battery it is. And this is the nickel cadmium battery. And if you look at the write-up, I said to mask the phone and the battery. And when you did that for this device, I don't remember the numbers, the battery weighs way more than the phone. So I talk about form is function is determined by form. So the battery is big, the phone's big. There was a big movement that occurred a little later on, phones getting smaller. And there, what you find is when kids had different phones, which was really true like 17 years ago, 15, 16, 17 years ago. It all changed in 2007 when the first iPhone came out. And now I haven't seen a kid with anything other than an iPhone in a long, long time. But one of the things I point out is that the efficiency of a phone battery, those phones 30 years ago, we'd be lucky if they lasted 8 hours. What caused that change? Now your battery can go all day and sometimes into a second day. And it's because of the lithium ion battery, which first of all has a higher voltage, second of all has a lower mass, so you get more electrons per gram, because every gram of lithium is more moles, because its molar mass is only 7, whereas nickel cadmium's molar mass, if you look up the atomic masses, they're in the 60s, almost 10 times more massive. So with the combination of those features, the greater oxidation potential of lithium and the more electrons per gram, because there are more moles per gram of lithium than nickel and cadmium, you get a more efficient setup. One of the things that's also fun to do, this I don't have pictures of this, is I like to ask a trivia question. I want to see, what's the most common element in the lithium ion battery? The most common element in a lithium ion battery. So you have an idea, Laura? It looks like you want to raise your hand. No? Okay. I wish I thought to put this in. I have some. The most common element in a lithium ion battery is number 1, copper, number 2, carbon, number 3, lithium. And it's not lithium metal. A lot of people think they're going to open a lithium ion battery and find lithium. But they're lithium ions. And of course, the unique feature, another unique feature of a lithium ion battery is that lithium ions actually move in the battery. In a battery of a dry cell made of zinc and manganese dioxide paste, which is the old cells that used to leak a long time ago, or even a nickel cadmium battery, those ions are not moving. They're too big to move, but lithium ions are small. So lithium ions move from one side to another. The structure of the battery is a jelly roll structure. So there's a layer of carbon. Here's a layer of carbon. There's a layer of copper, and there's a plastic layer that's a semi-porous membrane, and it gets rolled up like this. And that fits in a battery. Now the battery is actually much smaller than this, but the length of the copper sheet, the length of the poly, whatever kind of plastic it is, and the length of the carbon sheet is twice as long as this. That's all fits into, I have a AAA battery here. So this is not one. This is I have no idea what it's a standard Duracell battery. It's not lithium ion. But it's fascinating to see the engineering that goes into that. And you may not be surprised to know I've been driving a Tesla for a long time, so I ride on top of lithium all the time. And I always say copper is my favorite element. That's a long story, but one of the reasons is I can afford to have a kilogram of copper. I have a beautiful polished sphere of copper, which costs like $30, I think. I would love to have it in gold, of course, but a pound of gold, of course, would be out of my price range. But lithium is my second favorite element. Any other questions out there? Anybody do electrochemistry experiments? Okay, I see a question from Hegeman. Oops, it disappeared. How can I get the question back?
Hi, Frank.
There.
Thank you for your presentation.
Oh, here we go.
For a long time, I have been toying with the idea of actually introducing students at the honors level to electrolytic cells so that they can actually start by making those observations as what is being discharged at each of the electrodes.
Yes.
Introduce them to the redox reactions and writing those hat reaction equations first before moving on to the voltaic. And I was wondering if anyone here is doing that already. I haven't done that because of time restraints and also because of the way that the curriculum is organized at the honors level. We hardly ever start by talking to them about redox reactions or the movement of electrons.
Sue, did you have something to offer?
I do use, this is Sue Clemmer. I use some simple electrolysis to actually start my discussion of bonding for honors chem. I start with a YouTube simple electrolysis of with a copper chloride solution, so they can smell the chlorine at one side, they bubbles, and they can see the copper depositing on the carbon electrode, and we write some half reactions for that, and from there, just that qualitative kind of work is where we get to ionic bonding. And then from ionic bonding, we say, well, okay, can you imagine a situation where where there's not enough difference? What's making the electron go from one atom to the other? And from there, we get to Pauling and we get to covalent bonding. So I used to do a longer introduction to electrolysis at the beginning for my honors, but my course got shortened up in time and I don't have the amount of time anymore to do that. But I find a qualitative look at electrolysis to be the most direct way to get into bonding for me, because in my curriculum, chemical bonding actually doesn't come until the third quarter. We do a whole lot of other stuff before we get that's at the macroscopic level, before we get down to what's actually going on to make compounds change to other compounds. So yes, I do that.
Thank you. I wasn't thinking about this in terms of that, but we do in our honors chem course, the one I inherited from my predecessor, had been doing it for 34 years. He did quite early on in the year a lab demo of electrolyzing water from the point of just understanding the stoichiometry of the reaction, because you see twice as much gas on one side as the other, and it makes H2O make sense. We don't worry about whether it's a redox reaction. We come back, we circle back to that a lot later and say, obviously, look what happened. H2O is getting oxidized and reduced. But you can't make the qualitative observation. A fun thing to do, I don't know if anybody's ever tried doing this, is to electrolyze. The water in electrolysis setup has some sodium sulfate added to it, sometimes sulfuric acid, to increase the conductivity and speed up the reaction. A really fun thing to do is to electrolyze sodium chloride. I mentioned I did that when I was a teenager, but now I do it in the Hoffman apparatus, the two burette tubes attached to each other, kind of like an H-shaped thing. If you do, has anybody ever electrolyzed sodium chloride besides me trying to kill my family 60 years ago?
I've had my students, we do a guided inquiry electrolysis lab with my AP students.
Yeah.
Where basically I'm like, you need to make electrolytic cells. You need to make one that deposits a metal. You need one that makes a gas. You need one that makes gases. So sodium chloride is one of the choices I give them.
And did you do it in a quantitative way? Because you can see
no, it's just qualitative.
Okay. So if you do this using the Hoffman apparatus, which is what that H-shaped thing is called, you get a really curious result. You let it run for a while. On one side, on the cathode side, you get a significant volume of gas, but not on the anode side. The anode side is like minuscule. It's like you might have 10 or 15, and you'll have 2 or 3. And the question is, what's going on? And I would run this all day long and have students come back between classes to check the progress, right? To have a little data sheet. What time is it? What are you seeing? And eventually what you see is that tube where the chlorine on the anode side, where chlorine is being oxidized, turns yellow. Chlorine is quite soluble in water. And it turns, so the gas, and if you watch the bubbles, if you look more closely, you see the bubbles rising to the top. They don't quite get to the top. They dissolve as they're rising. So there's some gas, at some point you exceed the solubility of the gas and you will get some volume of gas accumulating. Really, if you're doing one, you can easily do the other. It's kind of a fun thing. It's hard to believe something I played around with as a kid in the late 50s is, I'm teaching it today. Any other questions out there? Challenges?
Was a question in the chat.
Oh, I'm not good at looking at chat.
That's okay. That's why I'm here.
Okay.
Someone asked about using Chem Collective and the virtual lab set up to do redox reactions there, and then at least virtually getting that information. I don't know if anyone here uses Chem Collective.
What's that called again?
Chem Collective.
I've never used it. I've heard of FET, but not Chem Collective.
Yeah, this is out of Carnegie. I think it's out of Carnegie Mellon originally.
I have to look that up. Anybody have
cool.
experiences?
There are a lot of really interesting virtual labs there. I've explored it, but I've not ended up using it with my students because there's a learning curve to getting going with it, and I just haven't had the time to devote to that. So it would be really interesting to hear if someone has been using it.
It looks like Mona has something to say.
Yeah, I was just playing with it as you were talking, Frank, because I was curious if you could run this reaction virtually on it. And I'm not sure if I can screen share, but I can show you really quickly how to do it on the Chem Collective page. But it was really neat. I saw the color change that you talked about.
Oh, really?
And you can monitor the temperature change on there.
Kristen,
and I know
do
sometimes you don't
sharing?
Yeah, I know like sometimes you don't have resources to purchase everything that you want. So
Right.
it might be nice to. Let me see if I can do that.
There we go. Oh,
Can you see my Chrome screen?
yeah.
And so it looked like, it's limited in terms of what solutions are available. So I picked electrochemistry as the topic here, and you can see there's a fair number of solutions available as well as solids, and they did happen to have the copper nitrate and the zinc. And it's nice because it has that blue color, and then you can just add zinc powder, and I just picked a mass to add in there. But if you look at the temperature here on the side, you can see the temperature going up.
Oh, wow.
Reaction happens. They'll probably have to catch the maximum temperature achieved because it starts to go back down and as it equilibrates.
Oh, neat. This is neat.
And you can see the solution is not blue anymore. So I thought that was kind of cool. So
wow. I'm gonna look at this more closely. I'm really interested.
Yeah, I actually have been using it along with doing labs in person. Like I feel like, especially with COVID, like students got comfortable with doing more things online.
Right.
And it was nice to have this as a complement.
Yeah. So thank you for pointing that out. Chem Collect.
Collective.
I'd love to hear more about your use of Chem Collective. Maybe we can find a platform for you to do that, or you could present to us in the future with NEACT, or there are other chemistry teacher groups. And I think some tips on using Chem Collective as a resource with your students, that would be really interesting.
Yeah, I used it to, when we were doing remote teaching, I made a buffer lab. So that worked out pretty well, like different ways of making buffers and measuring the pH of the solutions and testing capacity. So yeah, it's a pretty useful tool.
Thank you.
Yeah.
Anybody else got any novel observations or interesting things that are out there? It's really amazing what you can find out when you get together.
There's nothing better than being able to hang out with other chemistry teachers and share ideas.
The only thing missing is a beer.
Well, you know, you're home, Frank. You can have whatever you want.
I'm drinking H2O.
I got my coffee.
Yeah, I already been through a couple cups of that. So, but that thing with the sodium chloride electrolysis is really fun. The other thing that's fun to do is to, and I have not been as successful at doing this yet because I try to make a universal pH indicator. But what are the half reactions that occur in electrolysis of water? A lot of people want to write H plus an electron going to H2. And of course, that it kind of makes sense, but that's not what happens. It's H2O being reduced and H2O being oxidized at the different electrodes. But there's a pH change in each chamber. So when you have that, you have the cathode side and the anode side, you can see if you had a good universal indicator, one should be turning basic and the other should be getting more acidic. But I haven't worked that out yet. That's a future project before I turn 90.
So now I'm thinking about, you mentioned in your bio, Frank, that you do a lot with getting your students involved in research, you know, doing independent research projects. And sometime I'd love to have you tell us more about that and how you help students generate ideas.
Sure. You want a brief thing right now?
Sure.
So as you mentioned in my introduction, I had a research career where 20 years at Columbia, Yale, and Thomas Jefferson Medical School. And I walked away from it cold turkey because I wanted to coach my kids' Little League baseball team 25 years ago. And I was actually living in Connecticut, but working in Philadelphia where Thomas Jefferson was. I would go back and forth once a week. Why did I start this story now? I'm showing my age. What was that question you asked me, Kristen? Oh, if you're muted.
About helping your students generate ideas.
Oh, right. So I walked away from that research career cold turkey. And I taught 1 year at a high school. I found long story how I found it, short story how I found the job, but I'm not going to go into that. I taught 1 year driving 45 miles to, where was I going? Stamford, Connecticut on the Merritt Parkway. I don't know, anybody from Connecticut driven on the Merritt Parkway? It's not a lot of fun. But I did it for a year. Then I found the job much closer, 10 miles away at Cheshire High School. And then I found the current job I have at Hampton Hall. But by then I've been away from my research career for about 4 years. And I was busy doing high school stuff and coaching the JV baseball team because you got to do that, running an environmental club. And then one day in 2011, a student came up to me at the end of honors chem and said, "Hey, Doc, can I do a research project?" And I kind of said, "Well, research, you know, I haven't done it in a while. I'm not so sure." It's a long story, but a bunch of factors came together and I resurrected my previous research career, which was dealing with photochemistry and photochemotherapy with a molecule called sorolin, which occurs naturally in figs and other fruits, celery. And this kid had two parents who were doctors at Yale. One clinician and the other a researcher. And he discovered laying fallow in his mom's lab a device called a CELDI device, which I had never heard of. And he came back one day to school. I found a better way of studying our reaction using CELDI. I said, "What's CELDI?" CELDI stands for laser desorption ionization. We're studying some photochemistry. It's basically a form of mass spectroscopy. This kid did an amazing piece of work. We got involved with a previous collaborator I had worked with from Johnson & Johnson pharmaceutical company. And he spent a summer in their lab, which by then was down at Duke University. Long story, I won't get into that. And did a spectacular job. so that after working on the project for 6 months, he had a paper accepted for a presentation at an international meeting of photochemistry, American Society of Photochemistry in Montreal. And we drove up there for him to present the paper, him, his mom, and I. And he did a spectacular presentation. In fact, a senior professor who won a prestigious award came up to him and said, "Sir, you said you were a high school chemistry student." He said, "Yes." He said, "You should be a postdoc." This kid was spectacular. He's now an MD PhD student at Northwestern University. He's finishing up his 5th year of work. But that resurrected my research program. After him, there were a couple other students that followed along the way. And because of him, the school decided to kind of make an institution, something we call science inquiry and design. And I would have 2 or 3 students a year working on projects until my boss said, "You know, we're paying you a lot of money. You only have 2 or 3 students doing this. So we got to get more students." So I did an outreach to get students involved. And we have about anywhere from 8 to 12 projects a year submitted to Connecticut Science Fair. We're a small school. We're only 300 upper school students. So the way it's evolved is that the seniors do the research in the lab, where basically reproduce the mini university lab. And the other students do projects they can do at home, sometimes requiring some help from school. But we have a bi-weekly meeting where we talk about ideas, make them aware of deadlines for the various science fairs. We have 2 major science fairs in Connecticut, one at Quinnipiac University, one at UConn. And last year we had 8 submissions to the Quinnipiac Science Fair. And I think every student won some kind of prize. Now there are a gazillion prizes. They do a great job of getting money from industry and such. But it requires a big commitment of extracurricular time, because we don't count it as a course. So it's all done as extra work, and the kids throw themselves into it. Anything else out there? We have any other Connecticut Yankees in this audience today? I see lots of chat messages.
Yeah.
I like what, who said my kids say my labs are great? What do you mean by that, Rose?
Oh, just that, like Pete Epley was saying up there, how oftentimes the lab is designed, and I know that the kids aren't going to get like this fantastic result, but that's not the point. And I try to emphasize that starting in honors and through AP, I teach both of them, that it's not like what you get out of it isn't the point. The point is when we're done, can we talk about what you did well, what went wrong? What are some of the reasons that we didn't end up with what we thought we were going to get on the front end? And that's one of the ways that we get to tie in like stuff from other units, right? And get to look at the big picture, the error analysis. And so anyway, so they almost never get like a super result. And then the joke is that all my labs are rigged, but it's fine. They have fun. It's good. And it's a good thinking exercise at the end. So
I think it's more the process and exposure to experimental technique that is important.
Yes.
Of course, you don't want it to be a complete. If you got no voltage, that would not be good. If you didn't get any heat when you added zinc dust to a reaction, if it was 0 temperature change, of course you'd have to figure it out. And just that process is always helpful.
Yes, I agree. So we do a lot of that.
I'm looking at the chat questions, see any other things in there.
All right, well, it's been a really great conversation. I'm happy to keep it open for a while if people want to continue to talk and share ideas. But thank you so much for presenting today.
You're welcome.
A lot of us are intrigued about this lab and about ways to, I love these it pulls multiple concepts together, and, using your lab data to calculate something. It's just, it can be a lot of fun. And then, other ideas that come out of it, that's always really helpful. So
Yeah, I think that's the physical chemist in me.
yeah, I have a peak. I don't have as extensive, but I trained as a physical chemist, and so did my husband. So I always find those really cool to do.
Yeah.
And so I want to thank everyone for coming today, and thank Frank for presenting. We will be sending out at the end of the summer form for anyone who needs PDPs. I also want to invite everyone, if you're not already a member of NEACT, to join. If you are already a member of NEACT, we'd love to see you get more involved, maybe do some presentations in the future. So thank you for everyone for coming. And like I said, I can leave it open and we can discuss, but I am going to stop the recording at this point.
Let me ask you a question, Kristen. Are there files I want to share with people? I just get them to you and you can share them?
You get them to me. I can email them out to people.
Okay.
What I was going to do is link them into the document where we put all the summer PD things and just post them in there.
Because I have some, as I thought about like that picture of the unraveled lithium battery.
Mhm. Oh yeah, sure. We can.
Really fun to see. I'll share that with you. I had that battery is not easy to take apart.
Right.
I had a very big and strong senior student a couple of years ago who was determined to get it apart. I think it is important before you try something like this to work in a well-ventilated area. There are some fumes, and also wear gloves if anybody tries this before, because there's an electrolyte. I have no idea what it is, but there's a liquid that is present. So just err on the side of caution if you try it.
Always.